All right, welcome to the third episode of what I'm calling Bit by Bit. This is my exploration into low-level programming. I've chosen the Apple IIe as the platform because it's kind of fun, and yet it kind of exercises everything that you need to know from a low-level programming perspective. So, without further ado, let's just get started. So, this is me working through the assembly lines, the complete book by Roger Wagner. This is the book. Have it in PDF form as well. We're going to start with chapter 3 at this point, or continue with chapter 3, although I'm going to review it as well as continue on. What we've done so far with the book is we've rung the bell. We've done that by poking bytes into memory directly with the machine monitor, and then running that code. We did it in mini assembler where we typed actual assembly code, and we did it in a Merlin program. And we're going to kind of review that. And then we're going to extend on that, go a little bit further. So what do we know so far? Well, so far we know something about floating point basic, which is this this square bracket prompt. And then we know a little bit about integer basic with the angle bracket. We know the machine monitor with the asterisk, and we know a little bit about the mini assembler with the exclamation point, and a little bit how to run Merlin, this is a little redundant, sorry about that, but it is what it is. So without further ado, let's look at what we can do with this system right out the get-go. So this is review. If you went through the first two and this is boring, just kind of wait it out and we'll get on to new stuff. But right now, here it is. If we boot the machine with nothing in the drives, what happens is, and this is the enhanced Apple II, what happens is it boots to this screen here and we can't do anything. But if we reset it, which is Control F2, then it pops up with the bracket prompt, which is the floating point basic prompt, the newer basic. This one allows floating point. And you can code here. You can write code just like, let's see. You can write basic. And the other thing that you can do is you can call into the machine monitor, which is at -151. All right, and that gets us into this prompt where we can look at memory and see what's there and that kind of thing. And that's basically all we can do without additional stuff. If we had a real enhanced Apple IIe, we could possibly get into the mini assembler and stuff like that. But in this emulated environment, we can't without booting to a disk. So I'm going to boot to the DOS 3.3 master disk, system master. And we're going to it's going to look very similar, same prompt here, but it starts booting into the DOS instance. In this case, it looks the same, and it is kind of the same. I mean, the same sort of stuff works. Print hello. Oops, print hello. So it is basic, and it's floating point basic. But now we can get into integer basic by typing int, and that gives us this bracket, which kind of works the same way as the floating point basic, but it only handles integers and not floating point numbers, amongst other minor differences we don't care about right now, because we're doing the low level stuff. But we can call into the machine monitor this time the same way. Gets to the same basic idea, but this machine monitor knows about the mini assembler. So now we can go to the mini assembler. The way we get there is we go to F666, and we just go to that, call that routine or whatever, and there it is, we're in the mini assembler. To get out, we just have to call the machine monitor, which lives at FF, we need a $sign though, FF69. Okay, there we go. Yeah, except for that just shows us what's in memory. We need to go there, FF69, and we go there. That gets us back into this, and Control F2 will get us back to floating point basic, or sorry, gets us back to integer basic. All right, there we are back at integer basic. From here, we can go to floating point basic, or we can get back to integer, that kind of thing. We did all that in the last video. And so that's just a review of sort of the environment that we're living in. Let's ring the bell. And one of the ways we can do that is in the monitor. So let's go into the monitor. Column on this 151. And then we can poke bytes into memory. So at location 300, for example, we could put the bytes that we want, which is JSR, which is, oh boy, Now I'm trying to remember from memory. 20, and then somewhere to poke it to is FBDD, which we have to reverse the bytes, if you'll recall, and we'll kind of review that as well. But once we've done that, then we can RTS, which is 60. Whew. Let's see if that worked, if I remembered correctly. Yeah, it looks correct. So we JSR FBDD, which jumped to subroutine FBDD. The bytes are reversed because this is a little Indian environment where the little end comes first in memory. So we have at 300 we have 20, which is the jump to subroutine call, and then at 301 we have the least significant byte of the address. So it kind of flips them. Addresses are 16 bits, yes, 2 bytes. The first byte is DD, the least significant, the trailing end of the address. Okay, comes first at 301, and then at the higher address at 302, we get FB, which is the most significant bytes of the address. So there it is. It goes RTS to that address, and then to return, we just do 60, which is the opcode for RTS. So it's in memory. After that, some breaks. 0, 0, 0, 0, 0. Okay, and that just means if we try to run it, it'll only go that far. But since we got the RTS, it's not going to really matter anyway. So here's 300G to run it, and it beeps. All right. We could have done it in the mini assembler. If we wanted to do that, we would go into the mini assembler, which is F666G. There we are in the mini assembler. And then let's put it somewhere else. This is kind of, whoa, we're jumping way ahead, but let's do it anyway. We'll put it at 306. All right. And then we could just type JSR, FBDD, RTS. Well, we can't do RTS. We can only do JSR, FBD, one line. It gets assembled. And then we hit space to go to the next address that's available, and we type RTS. And we hit enter, and it gets assembled. And if we look at 300, or 306, but we'll look at 300 just to see what's going on. Yeah, we're done here. We could probably list it here, but let's just go back to the monitor, which is $F69. We'll go there. And now we'll take a look at memory, 300L. All right, we can see both our programs in memory, and they're identical. All right, the one at 300 and the one we just did with the mini assembler at 306. And we can run the one at 306 from here, 306G. All right, and then we can control F2 to go back to integer basic. And we can call into our routine at 768, which is 300. Okay, and it'll beep. And then we could go to 306 if we knew the math, all right, which I don't know the math, so I pull up a calculator and I just type 306. All right, and it gives me some really weird numbers. That's not the right number. What did I do wrong? Oh, 306 is the hex. I'm sorry. Got to be in hex notation. There we go. 774 is the decimal representation. So it's 774. So if we call 774, the new one at 306, it beeps as well. All right. So a little bit about that. We'll do some more math as we go, but that's the review. So what do we know in terms of assembly language? Right now we know 2 instructions. One is JSR and the other one's RTS. And we know JSR works by having an address, and RTS doesn't require anything. So that's sort of what we know so far. What we're going to know at the end of this is we're going to know a bit more math, but just enough to get by. We're going to know a bit of 6502 architecture. We'll look at that in the book, and we'll know 6 new instructions. All right, so let's get moving. So what's enough math to get by? Well, let's think about what we're talking about when we're talking about math in this context. All right, normally we have the digits 0 through 9. And we're achingly familiar with that. We're going to use in hex, we're going to add 5 new digits. There's going to be the A digit, which is in decimal is equal to 10. And then B, 11, C, 12, D, 13, E, 14, and F, 15. All right, so we're going to have that. But let's review what we know about bases. Not to go like make your eyes roll back in your head, but it's kind of important. Remember that we have numbers like 10 and 11 and stuff. And we immediately know what these mean. All right, 10 means that we've got one set of tens, no sets of units, no ones. All right, so there's 10 of them. And with 11, we got a unit and we got 10. And if we were to take and add another digit in our position system, we'd have 3 units here, 2 tens, and 1 100. So 123, it adds up. It's very simple. And then, 567, kind of the same story. We got 5 100s, 6 tens, and 7 units. And we're familiar with that from grade school, which is nice. And it translates really well to other number systems. Like, for example, let's take a 4-bit number, okay, from binary. All right, this is base 2. And what we have here is we've got 4 places of 2s. And this is where, things kind of go off the rails sometimes with people and trying to understand this stuff. So we take that first 0 on the right, and we say that that 0 is equal to 2, is equal to 0 times, if you will, 0 times 2 to some power of 0, so some power of 2, which is 0 in this case, because it's the first one. And that's a unit, and that's 0 times 1. So that's going to be 0. And let's 0 times 1, and that's 0. That's the first bit of math. And then the second one is 1, right? But that's really equal to 1, that's our number, times 2 to another power. In this case, it's 2 to the 1, all right, which is equal to 1 times 2. And that's equal to 2. Right? And this third digit is 0, right? And that's really equal to 0 times 2 to the second power, which is 4, right? 2 to the 4, 2 squared is 4. And if I mangle this, I apologize. I'm trying my best to explain something that's not very trivial. All right, but anyway, so 0 times anything is 0, but we'll play it out anyway. 0 times 4, and that's equal to 0. Right? And then the fourth one, the last one, is 1. And that's really equal to 1 times 2 to the third, which is 8. Right, 2 to the third, which is 8. So 1 times 8 is 8. So, but that's 1 times 8. And that's equal to 8. And if we add those up, we get the number, let's draw it out pretty, We get the number 10. Okay? So this binary number here is equal to 10. And we can think of it like this. This is the way I do binary is I go, this is 1, so that's 0. This is 2, so that's 2. And this is 4, and that's is none, so we're still at 2. And then this is 8, so 8 and 2 is 10. It's that easy, right? We can do another one. Just get rid of this scratch pad here. We can do another one, and we can say, well, what about 0, 0, 1? Well, that's 1, because this is the 1's position, and there's a 1 there, right? And this is 0. But then we could get a little fancier and do something like that. And what we wind up with is, well, we got a 1. We got no 2s. We got a 4, so this is 5. And we're done. It's 5. All right. We could do 0, 1, 1, okay, which is a 1 and a 2. That's 3. And a 4, that's 7. So this is 7, and that's pretty straightforward. And then we could do like this, 1, 1, 1, 1. Okay, like that. And we got a 1 and a 2, so that's 3. And an 8, that's 11. Because that's all we have with these four bits. Now, we said, well, there's these byte things, okay? And bytes are 4 and 4, and that's 0. And then we could do 0, 0, 0, 0, and then 0, 0, 0, 1, that's 1. And we could do 0, 0, 0. It gets a little tedious, but hang in there. 1, 0, 1, 1, which we already know is 8 plus 2 plus 1, which is 11. And it's still 11 because there's nothing on that left. But when we start adding stuff in up here, no 2s. That number is a little squirrely. It's hard to figure out. But we could do the math, and it goes like this. We know that 4 of these, if we look at it that way, we got 1, 2, 4, and 8. So this is 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So we know this part is 15, but then it gets kind of a little harder to calculate. But let's start at the right, and we'll count our way left, and we'll figure out what all those positions are. So the first one is 1. The second position is the 2s. The second position is the 4s, and then 8s, and then 16s, and then 32nds, and then 64s, and then 128s. So we got 128 plus 32 plus 15. But that's kind of hard to keep track of. And we're gonna spare you the details, but let's just say that you can break these up into two separate sets of 4, which we'll call them nibbles, and that'll give us some sanity, something easy to deal with, okay? Because we already know that this one is 8 and 2 is 10, okay? This is 10, and then that other side is 15. We know that already, okay? So that's if we were working in decimal. But we got this hex thing, and hex makes life beautiful because we can represent these with single digits, all right? And we can do that by looking at our handy dandy cheat sheet here, where we got the 0 is 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 is A, 11 is B, C is 12, and so on and so forth. So then we look at this and we go, okay, well, that's 10 or A. It's just A, okay? And then F, okay, because that's 15. And then if we were to look at this first one here, let's do it. Well, we know it's 0. That's simple. And then we got this 8 and 2 and 1 is 11, which is B. So that's 0B. And then this one's easy. This is 0, 1. Okay. So as long as we're staying in those, 10 or less, it's almost immediate answers. But if it gets into the bigger kind of squirrelier numbers, they're not too hard. Right? So that's just enough math to be dangerous. I hope that that's clear. And if I'm looking over there, it's because I'm looking at the notes. Sorry about that. But here we go. So next is a bit of 6502 architecture, and we're going to look at assembly lines in the book at page 409. So this here is page 409 of the assembly lines book, and it's called the programming model, and it's really the abstraction that we're going to use to think about how we interact with it. So when we're doing assembly language programming and stuff like that, we're going to be thinking about it in terms of, well, what's in the accumulator, what's in register X, what's in register Y, what's in the program counter, what's the stack guy going on, right? And the instructions that we use, like JSR, RTS, LDA, those types of things, they're going to work with the accumulator and registers to do work. So this is the kind of an important model and what we're going to look at. So there's 8 bits in most of the registers. There's 16 bits in the program counter, and there's some special stuff about stack pointer I don't fully understand yet. But basically with the accumulator, this is where we store the results of math operations, where we store numbers that are data that we're going to move around. We're going to put it in the accumulator or one of these other registers and then move it around. It's a really handy 8-bit location. So there's that. There's 2 registers called the X and Y registers that they're general purpose registers. We can put stuff in there and do stuff. There's some special things that we can probably do with them as well, but for the most part, we can just put 8 bits in there and take 8 bits out and do what we want with it. So we got 3 kind of registers available for our general use. And then the program counter is where, like when we call into FBDD, which is where, there we go. When we do this sort of thing and we call and we run this FBDD thing, that's where it lives. There's a program counter, a place where that address is stored and referenced. And when we go there, it means that it contains our address and starts executing these instructions at this location. Yeah. And then the stack is a special sort of thing. We can look at kind of how the stack works somehow. I guess we'll do it this way. The stack is a programmer's abstraction. If you're not familiar with it, let's do a quick review. So when you put things into a stack, like a stack of plates, it just looks like that. There's a stack of plates. When we put numbers in, though, we're going to put a number onto the stack, and then we're going to put another one, pile on top of it, and another one, 3, and then another one, and so on and so forth. And our stack looks like that. And it grows upward from whatever we put first to whatever we put last. And so if we think of it as what's available to us immediately, if I ask the stack, give me your latest value, it gives me the 5. And that's really the only access I have to it. I can get the 5, then I can get the 4, then I can get the 3, then I can get the 2, then I get the 1. So we call that last in, first out, LIFO. Okay, last in, first out is our way of remembering what goes on. When we put stuff onto the stack, we can really deal a deck of cards, 1, 2, 3, 4, 5. Whatever's on top is the one we can access right away. So when we're talking about the stack, that's what we mean. We're going to put numbers there, and we can get the latest number off first. That's all there is to it. Yep, that's what I wanted to say about that. And then there's this process static guidance register, which is 8 bits, of which only 7 matter. There's one that's not used in the MOS 6502. But basically, each bit represents a flag. If this bit is a 1, then there's a carry flag set. If this bit is 1, there's a 0 flag, and so on and so forth. And that's the whole model. So yay, we got it. Okay. Next up, we're going to look at this instruction codes. We're going to remind ourselves of what we know so far in terms of the assembly language, which is we know JSR and RTS. Gives us quite a bit of power because somebody somewhere already wrote a bunch of routines that we can use to get input and output and stuff like that in the Apple IIe machine monitor. Like the bell routine is just one of a whole slew of them. So we can leverage that. We can JSR to those routines. And when they return to us, we can use the values that they put into those registers and stuff like that for us. But how do we know what's going on? Well, we have this table in the back of the book that kind of goes through some of the instruction codes. Let's read this first bit a little bit, and then we'll look at these entries into the table. So it talks about the time is given in clock cycles. And this is this time field right here. And you see it's got asterisks and notes and plus and all that stuff. And all this stuff talking about here after this clock cycles in 1 microsecond at 1 megahertz bit is about the special considerations. And we don't care about any of them right now. So we're going to skip it. But basically, we'll look at this first one just to kind of try to understand. So for times with a plus sign, meaning it's got a plus on it, you add 1 if a page boundary is crossed. So apparently there's pages in memory. Yay. We'll learn more later. But if we don't cross a page boundary, then this number just tells us how many cycles, 4 cycles, okay, 4 microseconds. And then if it crosses a page boundary, meaning it has to go fetch it from some other page in memory than the one it's on, then we have to add 1. So it's 5 microseconds. And so that's interesting, but not really for us. We're more interested in what this table gives us, generally speaking. So let's, instead of just kind of trying to understand it, let's go look for our entries. So JSR is one of the ones we know about. And interestingly enough, it's a fairly complicated thing to understand what the table's telling us. So it's a good one to start with a guide who's suffered through this several times. This is take 4 of this part of the video. But basically it says, what's the name and description of the opcode? And the opcode we're looking at, the one we know, is called JSR. Okay, jump to subroutine. And then what's the description? Jump to new location, saving the return address. And it took me a bit to understand, so hopefully this will help you understand. The operation is described concisely right here, and it is accurate, but confusing to newbies. All right, and then there's the addressing mode that's in operation here. This JSR thing only does one kind of jump, and it's an absolute jump. We say FBDD, that's where it's going. Okay, thankfully that part's easy. All right, it is the actual language that's used. What we typed was JSR dollar and then FF, the most significant byte, and then the least significant byte, the FF, baby FF. All right, so we said $FBDD, where FB was the major, the high order byte, and then the DD was the least significant byte. All right, the opcode that's in operation, which is what the JSR is a mnemonic for, so we don't have to remember 20, is 20. So if we see a 20 over here in our machine code, that means JSR always, okay, as far as machine code goes. Now, could it be in a data section and not be interpreted as JSR? Yes. But if it's machine code that's going to be executed, 20 just means JSR. And then the next 2 bytes are the least significant byte of the address, the most significant byte of the address, always. So as soon as we learn this, we can recognize this in any machine language program, and we know what it's doing. It's just a tool, a mnemonic, to remember what these bytes mean and what they are. Okay, and then it tells us that there's 3 bytes to this instruction. Sure enough, there's the 20, the DD, and the FB. And then it takes 6 cycles, 6 microseconds for it to get to do all the things it's going to do, which is kind of interesting. It gives us some very precise timings of how things work if we were to care enough early on. We don't care right now, but later when we're making games and graphics and stuff, we'll care about how long it takes. Okay, but not right now. And then the processor status, which it conveniently breaks down into the flags that it affects. In this case, none of them. All right. So now let's talk about the hard part, which is this stuff over here. It's going to deal with, it's got 3 things besides numbers, or 4 things besides numbers. It's got the PC, which is the program counter, the whole 16 bits. And then it's got the low byte of the 16 bits and the high byte, PCH. And then there's these arrow things, which I'll try my best to explain. But let's remind ourselves of what we have written so far. We've written these bytes. We see them over here in the emulator, 20DD, FB, and 60. All right, and they translate out to this assembly language, which we kind of trapped down here. But basically, when our program's executing, our program counter is pointing right here. Actually, let's change this. Maybe this to program counter is pointing to this location right here, 0300 when it starts. So the program counter is pointing at 300, which is what we told it to do. We said 300G, okay? And it said, okay, let me load 300 into the program counter and then start doing things. And so when it's at 300, it's going to get that 20. And it's going to interpret that. It's going to go, oh, that's JSR. What are the next 2 bytes? And it's going to go, well, the low order byte is DD and the high order byte is FB. And then it's going to do whatever that instruction is. And when it gets done with that, it's going to do the next instruction, which is 303. And so right now we've got program counter set as 300, meaning that the high byte is 03 and the low byte is 00. That's our starting proposition in understanding this next bit. And then it says, well, JSR is going to bump the program counter by 2 and store that onto the stack. Okay, that's what this sort of PC plus 2 with a down arrow means. And so what does that mean? Well, that means the stack over here, this is the stack, I guess, is going to get PC plus 2. Well, PC is 300, PC plus 2 is 302. So it's going to get 0302. Maybe not in that order, maybe it's 0203, I don't know, don't care right now. But it's going to have this address is going to be on the stack. That's all that first bit means. Then the second bit says, well, let's load the program counter to, we're going to change it because this is jump to subroutine. So the program counter's got to change. So what we're going to put where is we're going to put program counter plus 1 into PCL. So the program counter plus 1 is 303. It's going to put DD into PCL. So you could think of it this way, right? It's done that. And then it's going to do the next bit, which is program counter plus 2. It's going to put the PCH. So program counter plus 2, which is FB, it's going to put that in PCH, FB, which looks remarkably like FBDD, right? Okay, and then it's going to jump there. So it's going to go to FBDD, and it's going to do whatever FBDD does, okay, which is beep, beep, and then it's going to figure out how do I get back to where I was. And it's going to get that off of the stack. And it's going to go, oh, I need to go back to 302. Well, it goes to 302. It sets that to the program counter, but then it increments the program counter. So it sets it to 303, which is our RTS instruction. And so it gets to 303 after it beeped, and then it's going to return, which gets it back to us in the monitor. All right. Okay, take 4 on that. Thank you. That was kind of fun. All right, but that's that. That's the basics of that. We're going to go and move right on now, finally, into some new instructions. And the new instructions that we're going to learn are these. This is what Chapter 3 is going to cover in the kind of the second part, which is the LDA instruction, LDX, LDY, STA, STX, STY. And we can look this up in the manual. I encourage you to do that, but I'm not going to do it right now. What I'm going to do is we're going to get into the monitor. Monitor, call -151. And we're going to look around in memory and see what we got so far. We've got a couple of calls of these subroutines, and we're going to play around with LDA to start with. Okay, we notice that there's two ways of referring to LDA. There's this immediate way, and then there's an address way. So, well, I guess we're going to have to look at the manual because we need to know what LDA is. Okay, here's LDA in the manual. It tells us that loads memory into the accumulator, so we should try that. And then we're going to use this immediate version right here, not one of these. And that one in the assembly language is going to look like LDA pound dollar and then some byte. Okay, and it tells us that the opcode is A9 and it takes 2 bytes. So we can do this. We're just going to write over our 300 address, and I'm going to say A9, and then I'm going to give it some numbers, a hex byte. And in this case, FF is good enough for government work, good enough for me. All right, and then after we've done that, we're just going to kind of kill everything. We're going to put zeros in. Okay, so there we go. Now let's list it and see what it thinks it has now. It has an A9FF, which translates to LDA pound dollar FF. That's an immediate load of the accumulator with FF. All right, and then some breaks. Okay, so we're going to ignore all the cruff that follows our stuff. What we're concerned with is the A9 and FF, and we put a 00 just so things don't keep running off in the memory. All right, so we've created this LDA call, and we've said load immediate FF into the accumulator. Well, what the heck? Accumulator, where's that? Okay, well, the accumulator has an address in memory, just like this 300-bit, and it's 45. Right, so 0045, I think so. Yeah, and but that's not very informative. Okay, there's a trick to the monitor that lets us look into what the registers have in them. And that's if I press Control E and then enter, and it shows me the registers. And you can see right now that A has 98, which is, we could look in memory if we wanted to, and we could actually look at these bytes. So what we're looking at is what we got, A98, X24, and then blah, 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 blah. But we could just look at it like any other memory location. We could just do 45.55. Sure, we could look at that. And we can see that there they are, 98, 24, D8, 00, 10, and so on and so forth. All right. And so, yay, good stuff. And that's kind of it for that. Let me see what else did I want to say about that. Oh, LDA. Okay, so back to our program, 300 up. Okay, so our little program that we just wrote, A9FF, which loads the accumulator with FF, is ready to roll. If we call it, it'll do whatever we ask it to, the A9FF, and then it'll break, which is good enough for us. So we're going to run it 300G. And when we do, because we did break and not RTS or something, it actually auto dumps the registers. So we can see that putting FF into the accumulator was as easy as A9FF, and there it is. And we could change it. Let's do this, 300 A9 BB. That's perfectly valid, and it already has a break at 302, so we don't have to do anything more. We can call it 300G. And now A's got BB. So I think that's pretty straightforward. Let's look at LDX, because we can put stuff in this register, the X register, and the Y register, or the A register. And the way we do it is we look up our handy dandy instruction set list here, and we look for the one that says immediate. And this is, we could type it in as LDX, pound, whatever, but we don't need to. We're going to use A2 instead of A9. And if we wanted to do LDY, we do A0. So A2 and A0, A9, those are our bytes that we could poke. So we're just going to change our code from A9 to what, A2. That's going to put it into the X register. And we'll put 33 in there. Why not? It's already got, at 302, it's still got a break. So we're going to run it. And we got 33 in the X register. All right, so again, we'll just modify, whoops, not 300. We'll just modify what we got. Instead of A2, we're going to put A0, which is load the Y register. And we're going to load it with, 55. Okay, and if we didn't believe that we had a break already, we could just add one. Okay, and then we could just run 300G. It's going to break into the debugger, if you will, and it's going to show us the registers. And sure enough, Y's got 55. So we know how to immediately put stuff into the 3 registers. That gives us 3 new instructions we can mess around with. A9, A2, A0. And if we wanted to, we could do the same story over in the mini assembler, but there's really no point other than to satisfy ourselves that it works. So let's go ahead and do it anyway. Thanks, G. We go into the mini assembler. Well, okay, when it doesn't want to do quite what we want right there, which I'm pretty sure that ought to be right, we're just going to restart the emulator. Control F to, yeah, no, we just wait for it to boot. And then we're going to type integer to go into integer basic. And then from here, we'll call into the monitor. And then we can go F666, G, and we're in the mini assembler. Okay. And we'll do that. Anytime things aren't working quite how we think they ought to be, we can just reboot. It's the easier way. And later, as we get more accustomed to the environment, we can figure out why it's not work, why it didn't work. But for right now, easy enough. Go reset. But let's do the same story we just did, but we'll do it with the mini assembler. So in 300, in the location 300, I can do load accumulator. And then just like it shows here, I can do pound, dollar, and we'll put 11 into the accumulator. All right, and we'll hit return, which will assemble this, and we get A911. Okay, so that's that. And then the next thing we'd probably want to do is break. So I don't know, let's try break and see what happens. I hit a space, so it gets the next address, and then BRK. And sure enough, that works. Okay, let's see if we can run it from the mini assembler. I've never really tried that. So what we think we want to do is we have to do a hex value 300. That's where we want it. And then we're going to go. Okay, it works from there, but it put it back, but it did bring us back to the monitor. So may as well just go back to the monitor. So there it is. And it put 11 into the accumulator. So yay. All right, we'll stay in the monitor for the rest of the exploration. But let's see where we're at, what we've done so far. We did LDA immediate. We did LDX immediate. We did LDA, LDY immediate. But it says we can do an address. So let's figure that out. All right, so let's look at our memory. Just kind of see it right there. That's the easy way. We see there's nothing in memory. So we're going to put some bytes in memory, and then we'll use those to load from that location into the accumulator. So 310, it's available and it shows up on our screen. So let's just put something there. 310, we'll go ahead and put a few bytes. So let's put, and since the accumulator's already got 11, we'll not start with that. We'll put 22, 33, 44, 55, 60, and then 00, just to be sure it's all clear. And then we'll do 300L just to see where we're at. Okay, there we go. All right, it doesn't know how to decode some of these bytes. That's okay, we don't care. It's just data. So 22, 33, 44, 55, and 66 are all kind of contiguous together. All right. So we can pick one of these to stuff into the accumulator. And right now, if we do Control E and enter, we can see that the accumulator has 11. So let's pick like the byte at 312. That's the one we want to put into the accumulator. All right. And we go back to our manual. And we look at the load accumulator. And we look for the one that says absolute. All right. And we see that we could do it in the mini assembler as LDA, dollar, and then some address. Or we could just do AD and then 2 bytes of address like we've been doing. So let's do that. We want to do we're going to mess with our code at 300. And we're going to say AD, that means load accumulator with the bytes, the address to follow. So we know that we want to put 312 in there, but we have to put it with the low order bytes first, 12, and the high order bytes second. And then we can put the break just to be sure. Okay, so that's telling the accumulator to load from 312 into the it's telling the Apple to load the bytes that it finds at location 312, which is 44, into the accumulator. The accumulator currently has 11, so that's gonna be our code. We can look at it again just to see what's going on, and we can see that it's sure enough it does LDA $0312. Okay, we reverse the order of the bytes because that's how they have to be. Okay, because 300, the lowest memory location is what's going to execute next, which is the LDA. And then it's going to get the low order byte first, so the 12, and then it's going to get the high order byte next 3, and it'll figure out that's 312. Okay, and then it's got a break. So I think we're ready to run. Let's run it. There it is, and the accumulator has 44. So now we know how to do that. Well, let's put a number into LDY, right? So we're going to go 300 colon, and then which one do we do for LDY? Well, we look for LDY immediate. It's A0, and then the address, which let's pick an address. I want 66 in there, which I know is at 314. Okay, so I'm going to put the 14 and the 03 and the 00, and then we're going to run it, and we're going to expect that the I guess we're doing Y. Y is going to have 66 in it. It got 14. How did it get 14? What did I do? A0. Oh, A0 is an immediate add. So let's retool. So 300. We'll stick with the Y for right now. We're gonna go to the absolute of it, and that's AC. So AC, and then we can do 1403. 00, which is at 314, which is 66. So we expect 66 to go into Y next if we run it. Let's hope that happens. Yes, it did. Okay, and lastly, just to kind of close the loop on this LD stuff, we'll do LDY, and this time we'll do it right. We'll look at, we'll do LDX. We'll look at LDX and we'll look for absolute, and we know that that's AE. Okay, and some symmetry tells us that this is going to be AE 14, and then we pick something. Let's get the 55 out of 13, out of 03 through out of 313, and put it into X. All right, and let's hope I typed it right. Let's run it, and yeah, X gets 55. So that's 3. Wow, that's a heck of a progress on this. Let's see what else we got here. All right, we did those 3, and now we've got 3 simpler ideas of how to store an address, store the accumulator, whatever's in the accumulator now, into an address. So let's take a look at memory, and we'll start. Let's zero out all that memory at 310. So we're going to go 310 colon, and we're going to go 00, 00, 00, etc. Until we think we've cleared enough, and then we'll do list it again to make sure it's clear. That looks good, and we'll start stuffing these bytes into. We'll start stuffing bytes into 310, 311, 312 for the accumulator X and Y. We'll all do it all at once. We'll rewrite this 300 program to write to these addresses, and we'll do that by looking at the book. We'll go down here to where it says store. There's stored to the accumulator, store to X, store to Y. We see that there's all kinds of ways we could call it. We're going to do absolute, okay, for each of these. So these are the 3 byte codes, 8C, 8E, and absolute 8D, okay? And so let's store the accumulator into 310, and then we'll store into 311, we'll store X, and then to 312, we'll store Y. We'll take whatever's in those registers and put them into memory so we can look at them in memory. So the easy way to do that, 300 colon, then we pick the first one. Store the accumulator absolute is 8D, and then the address that we want to put whatever's in the accumulator. And we know that we wanted it to be in 1003. And then we wanted to store X. So store X absolute is 8E, here 8E. And then we're going to go 11, 311 is the next address. And then we're going to go do the last one, which is store Y, which is 8C. And that's going to go in 1203. And then we'll do the break. So we did 3 assembly instructions. Let's see if it worked. I was off somehow. Okay, we got store the accumulator into location 310, store the X register into 311, store the Y register into 312. Let's run the program and see what happens. All right, and now we know what the A register has is 44. X register is 55 and the Y register is 66 because that's what we set them to way back when. But let's take a look at memory and see, is that what we got? 44, 55, 66. Indeed it is. And if we wanted to just view the 310 to 312 thing, we can just do 312. And they're there, 44, 55, 66. So yay, that is pretty much kind of the section 3 stuff from the monitor perspective. Let's move on. We're going to do it in Merlin now, and to do that, we're going to have to load up the Merlin disk onto into drive 1, and we'll load the Merlin work disk into drive 2. So here we go. We're going to load that one. We'll load this one. There we go, and we'll reboot. Yep. All right, and it loads up Merlin. And we're going to use Merlin to write a program that does basically what we just did. We're going to store some direct data into the registers, and then we're going to move those into memory, and then we'll take a look around. So without further ado, we have booted Merlin off of its disk. We want to change the drive to our work disk. So we hit D for drive change, goes to drive 2. And then we can edit, because we've not done this before. We're going to go to edit, and it's going to go into the editor. The editor, remember, has add mode, A, I for insert, Q for quit, mon, and there's some other commands that we'll explore. But basically, to get into editing, we're going to go A. It's going to go to line 1. We can do Control P to get a line of asterisks, hit enter. We can hit space and Control P, and we get the outline of a box that we can put our stuff into. And we're going to write a program to mess with regs. Yeah, that seems reasonable. And then Control P, get another line of those. You can leave lines blank, but the editor's kind of squirrely on that. So probably if you want a blank line, just put an asterisk to indicate a comment. And then we have to set the origin and the org mode in this version of Merlin. Later, when we go to the full screen editor, that won't be the case. But for right now, we're going to go org to set the origin, and then we're going to set it to hex 300. And then we're going to set the word object thing into 300. That lets us run it from within this thing. All right, and we'll do this another asterisk thing here. And then what we want to do is we want to load the registers and then bail, kind of return. Yeah, we're going to effectively load the registers, copy those into memory, and then bail. So let's do that. Well, we can put a little comment that says load the registers, load regs. And then the load regs is, if we go back to our manual, we find these LDA things, okay? So we're gonna hit space because this is not a label. And then we're gonna give it that command. So we're gonna load the accumulator, and then we're gonna load it with a number. And let's just put 11 in there for now. So load accumulator immediate, we look on the thing and it says, oh, pound dollar something. So pound dollar tells it it's an immediate value, and we're going to put 11 in there. All right, we're going to do LDX, even though technically I think maybe the Y register comes first, but I don't know, neither here nor there. We're going to put LDX, and then we're going to do, we're going to put 22 in here, $22. And then we'll do LDY, $33. The reason I picked those numbers is because they don't generally occur randomly, and it's easy to keep track. So by doing this, so far we've put 11 into the accumulator, 22 into X register, and 33 into the Y register. So we'll put another blank line, and we'll say, okay, save regs. And where do we want to save it to? We're going to put it, we know that we can put it in 310, so 310 to 312 seems like a good way to do it since it already worked. We'll do that. And to do that, we're going to use the store instructions. And you can already tell how much easier it is to keep track of this than poke it bytes into memory, but there's value in both approaches. So to store the accumulator into memory, we do sta, and then we look over here to absolute. We see, oh, we just put the address after in hex, and we don't have to reverse the bytes. So we know we want it in 0310, right? Yep, seems reasonable to me. We'll hope it works. All right, and then store X into 311, and then store Y into 312. Seems right to me. All right, and then we need to bail, which I don't know. I guess I'm not sure what to do here. Probably RTS. Is RTS right? Yeah, what's right? See what happens. We'll put RTS there. And then we could do the check something so we would know, but this is definitely code we wrote, so the checksum won't really match anything else. Is that it? I think that's it. Oh, no listing. We probably will turn off no listing, but we will leave it right now. We'll turn off the listing later, but after we see why it's annoying. I think it's good. So there it is. We can list what we've done. It looks like it ought to work. Who knows? We're going to type a symbol to assemble it. We don't need to update the source because we just wrote it, so nothing to do there. It assembled, no errors, 16 bytes, and it looks like it might work. Okay, yay. Before I blow up the machine or something, I guess, we can save it. So, well, yeah, I think so. So we're going to exit the editor with Q. And then I'm on drive 2. I'm going to save the source. And what are we going to call it? We're going to call it playregs. Okay, it's saved. It's safe to mess with now. So I go back into the editor with E, and we can list it again, just to be sure. It's assembled, but why not do it again? All right, update source, no. It assembles, and oh, because we didn't have any symbols, the listing's not a big deal. All right, so normally it would show us the symbol tables. So for right now, we can leave it with the listing. It's not hurting anything. But there it is. We could run it here. I forget. Oh yeah, we can go into the monitor. And now we're in the monitor. And let's look at our program because it's loaded there. And sure enough, it says LDA 11, LDA X 22, LDY 33, store 310, store 311, store 312, and then bail. Yeah, it seems like it's going to work. And we can try it. We can run it. So let's do it. 300G and see what happens. Okay. There it is. Let's see what happened to, oh, we see in 310, there's some kind of program that we don't care about. So let's list it and see what's going down. Did it change? 310 is 11, 311 is 22, 312 is 33. Yeah, it worked. All right. And I think we can do the same 310 to 312 stuff we can do in a normal monitor. Yeah, 11, 22, and 33. So yay, it worked. We saved it. What else do we need to do? Well, we need to get out of this thing. How do do I remember how to get out of it? I don't know. How do I get out of it? Control F2, we can try it. Oh, please don't break. Okay, came back to here. Let's go. Control F2, reset it. Probably not ideal. We'll figure out normally how to get back from the editor back to the assembler. I just don't remember how to do it, but I'll make a note next time. But let's go into the editor and see if it's got our stuff. List, yeah. Okay, our code's still there. Yay. We'll assemble it because I don't know. We'll just do it because we can. All right, there it is. And then we'll quit the editor, and we can see that it has our source code and our object code, 10 bytes. 10 bytes is what? 16 bytes, okay, because it's hex. So it's 16 bytes, which is what we saw in the listing, or in the assembler. It assembled 16 bytes. And so it's got our code. Let's save the object code, which is O. And we'll say play regs. Yeah, sure. So Y for yes. And then we'll do catalog to see it on disk. And we see playregs.s. That's our assembly code. Playregs, our binary one. There it is as well. Now I can hit return to go back to the main menu, and I can quit and go back into like the basic world, okay, the DOS world. So I can type catalog here, and we can see that, yes, there it is, but we can run our code from here. So brun playregs, not that it's doing anything interesting, but we could run it, and then we could look at memory. Yeah, we could poke and peek. That'd be psychotic, but we could do it. Let's see, print. We'd have to know, oh, and I meant to show you this. We'd have to know the translation of 310. So we're going to go to the editor. We're going to make sure we're in hexadecimal, type 310. So 784 is the decimal equivalent of 310. So we can do print, peek, and then what the heck was the number? I don't remember. 784. Okay, 784. 784, and we should get 11, which is 17, yeah. Which is 11, which is 10, 16 plus 1 is 17. So yeah, it worked. And then we can do print peek, 785. And that would be 34, which is 22. 2 times 16 is 32, plus 2 is 34, yep. And then we can do print peek, 786, which is 33, which is going to be like 31 or something. I don't know. Let's see, 786, 51. Okay, so 3 times 16 is 48, plus 3, because we said 33. Yeah, 48 plus 3 is 51. So yeah, it worked. And we did it from basic, which I didn't plan. But that's it for this one. Okay, we have covered in quite a whirlwind tour how many pages is it? 2, 4, 6, 8 pages of chapter 3. I hope this was helpful to you. It certainly helped refine my understanding. Thank you.